Hi, I'm Helen Durand in the Department of Chemical Engineering and Materials Science at Wayne State University. And this is a set of tutorials on quantum computing for control engineers. And this is the first part. Please note that in this tutorial, we're going to be using some Jupyter notebooks throughout the series. And so if you would like to be able to follow along, then you're welcome to have that installed. I have Miniconda and I'll be using Jupyter Notebook and I'll have the Conda Forge channel, but you do not have to follow along. Anything that you do in following along is at your own risk. You can totally just find the codes that are at the bottom of this screen and then be able to just read them if you don't want to participate. So what are we going to cover in this tutorial? So the topics are first in this part one, we're going to have background and introduction to closed quantum system dynamics. Then we're going to have a tutorial about quantum state simulation with and without measurement using Python, including NumPy. Then we'll have some discussion about quantum algorithms and how you can do a base code with NumPy. Then we'll talk about starting to use Qiskit, which is an IBM, like for using the IBM platform for accessing their quantum computers. There are quantum computers from other manufacturers as well that you could go use. This is just one example. We'll have some discussion about what is noise in quantum hardware and how you can see that play out when you run simulations with the hardware, and then or run circuits. We'll briefly discuss some of the principles of what's called Grover's algorithm, which is one of the quantum computing algorithms that is somewhat famous and very foundational. And then we'll talk about how you can do a simulation of what the circuit would produce using NumPy. So this is the first part of the series, and so I'm going to be describing just some overarching aspects about quantum computing. And so though this tutorial is generally geared toward control engineers, I am a process control engineer. So I want to talk briefly about how quantum computing is being used within process systems engineering. So there has been a lot more attention in recent years on quantum computing, and they are a new class of computing devices currently under development. And in many respects, they're experiencing a lot of development. So that is one of the reasons that people have been interested in understanding more how these might be useful in engineering applications. And then there's also the sort of theoretical concept that they have potential for speed up for certain problems like finding prime factors of a number. So as a result of some of these different aspects of quantum computing that make people optimistic that maybe it will be useful for some type of engineering problem, or that maybe if we work at trying to find the uses, we'll find some good ones. People have been trying to look at various use cases of quantum computing and engineering. And so a lot of that has been trying out quantum computers for different domains or different problems, like, for example, optimization or machine learning, process design, chemical materials modeling, and then also control systems. And so control systems is my domain of expertise and so therefore of interest. So how do control systems and quantum computing intersect? Well, in today's control loops, this would be a typical example of one of those. We will have our process and there will be different ways that it changes over time according to its dynamics and any disturbances or inputs. And so we'll measure some aspect of the process, we'll call that an output, using a sensor. And then here we have the set point for the system, which is the value that we want the output to take. And then there's this error, which is the difference between the set point and the measured value of the output. And then there is the controller here, which executes some type of algorithm, and then it tells the actuator what to do. And then that will cause an input to be applied to the process and have an effect. So the thought is if we use today's computers for various aspects of this, but including, for example, this control algorithm where we run it on computers, should we use quantum computers for any control tasks? And so there have been a lot of examples of control engineers using computing advances to be able to do new things. And so, for example, over the last decade or so, there's been a lot of interest in trying to use machine learning in control. in different ways, handling, for example, unknown process dynamics or speeding up a control law. So we want to ask, if quantum computing is a new computing advance, is there any way that quantum computers can help with control? And so if the answer is no, that's helpful to know, and we don't need to keep spending time on it. If the answer is yes, then that's exciting. We have a new tool in the toolbox that can help us do something. But before we can try to answer any of those types of questions, we need to understand how quantum computing works. And something that's pretty cool if you're a control engineer is that a lot of the principles behind quantum computing can really be explained from a lot of control principles. But where I want to start is assuming that the audience might be a little bit like me and they're chemical engineers, process control engineers, for example. I want to help bridge the gap between what you may have learned in your past, which would be things that probably were in some type of chemistry class about quantum mechanics, and then what we're going to be using in this tutorial. And so as some reminders, if you took a quantum chemistry class in your past, you probably learned about the time-independent Schrodinger equation, which is really this eigenvalue-eigenvector relationship that's shown here with a Hamiltonian and a wave function and the energy as an eigenvalue. And then the time-dependent Schrodinger equation, which is shown here, and it involves time evolution of the wave function. Now, the wave function of a quantum system like an electron is going to contain information about the position of the quantum system. So for example, the wave function of an electron has information about the position in the sense that if, for example, you specify x0, t0, and you compute this quantity here where the star represents a complex conjugate, then this will convey the probability that the quantum particle will be found in a spatial interval with width dx around x naught at time t naught. And so this is then very important if you want to understand position for dealing with things like orbitals in molecules in computational chemistry. So wave functions are the position representation of the quantum state. And so if we want to try to not necessarily work in the position representation, and if we want to work with this idea of a quantum state, we can represent the quantum state as a function of time. And so we use this weird notation here called bracket notation. And so here we will have a very similar set of equations that represent for the quantum state, this eigenvector eigenvalue relationship, and then the time-dependent Schrodinger equation, really just the Schrodinger equation, which is shown here. And so in this case, this ket psi is the quantum state, and so this is Dirac notation. And so wave functions are related to the quantum state in a way that makes them good for representing information about position. But when you have position, you can take any value of a position. And so in general. So when we're working with computing, we generally want to try to start by thinking about the way that classical computers work. So they use these binary concepts where you can be in state 0 or you can be in state 1. And so position is not so convenient for trying to do that because if you can take a lot of different values of position, it is potentially harder to work with when you're trying to design something to work in binary. And so instead, when we try to get two possible classical states for a qubit, we don't generally use a wave function representation of the quantum state information in quantum computing because we are not usually so interested in the position of something. Usually we're interested in other observables. And so I want to emphasize that because moving forward, we are not going to be working with wave functions as we describe quantum computing. We are going to be working instead with the quantum state. And I just wanted to clarify before we keep going that this does not mean that the quantum physics, that if you learned it from a chemistry class, that you learned it wrong or that this is different. It's just that we're trying to think about different observables, and it happens that the wave functions are very useful if the observables you care about are related to position. But here, if we're interested in other observables, it's more convenient not to work with wave functions. And so a quantum algorithm, as I said, is going to be very related to control. So you might say, in what way? Well, a quantum algorithm is a manipulation of a quantum state over time that moves the quantum state to a final condition at which, if you perform a measurement, you can learn something about the solution to a computational problem. And so if you think about this definition, if it's a manipulation of a state over time, that sounds a lot like control of a dynamic system. And I want to make that analogy here. So here is a typical dynamic system that we might learn in a beginning linear systems class. So it says dx dt is ax plus bu. We have a state, which usually in engineering problems, is going to be a vector in the reals and then an input, which usually would be a vector also in the reals. And measurements don't affect these dynamics. We can measure our system and or measure our system state, and it will keep evolving. Now, let's consider how we can write a dynamic model that describes the time evolution of the quantum state. And so this is just the Schrodinger equation. On the prior slide, I had still had a partial because it shouldn't be a partial. It was just a carryover from trying to make sure that people understood that the form that you have seen in your past, if you have taken computational chemistry where the wave function is a function of two variables, you essentially get the same thing when you move to quantum states. It's just now it's a function of one variable. So here I'm being more explicit about that, trying to make sure people can understand. It really is a function of only one variable when you're working with the quantum state. It is not a function of two variables anymore, or multiple variables. So here we have d psi dt, and it is equal to, and on this right-hand side, this all here is going to be our Hamiltonian. And so you might say, what are these two pieces? Well, this piece would be a drift Hamiltonian, and this piece will be a control Hamiltonian or driver Hamiltonian. But what is more important than worrying about exactly where did this come from, it comes from different energy operators for the system. But the important thing is you could rewrite this expression here in this form. And so if you look at this form, it is not exactly a one-to-one against the form that's on the left-hand side, but I think what it's meant to do is help you say, hey, look, I have some operator times the state. So the derivative of the state with time is equal to some operator times the state, which is very resembling this, plus some stuff multiplying an input. Now you could say, well, that some stuff on the left-hand side is a matrix, and over here it's like this operator, but also the state. And that is fully true. So it's not a one-to-one relationship, but what this is meant to do is help people who have never seen um, the Schrodinger equation, or maybe have seen it but haven't really thought about this parallel, is as we talk about time evolution of the quantum state, it is not something that is like radically crazy. In principle, it looks very similar to dealing with a linear system's state evolution. It's just there are some differences. So besides that, this term is an operator times the state times the input. The state here will actually be in the set of complex numbers. So our input here can be a real number. And the weird thing, the really weird thing, is the way that measurements impact quantum system dynamics. So they create additional dynamic behavior. And so we're going to talk a little bit in the next tutorial then about how you can try to make a base case simulation of a quantum system evolving in time. Now that you've kind of learned a little bit about that, we'll do it in the absence of measurements to start. And we hope you'll join us for the next tutorial in this series related to quantum computing for control engineers. Thanks so much.